Today we are coming to the filtering. Last meeting we have finished about the circuits. Okay, so on Monday we finished the bridge circuits and divider circuits, the Wheatstone bridge. Now we are coming to the RC filters. So RC is basically resistor and capacitor to filter some noise, either it is in high frequency or the lower frequency. There can be low pass RC filters, high pass or band pass or band reject RC filters. You can also read this in more details in the books. They are all available. I will strongly suggest you to read the books in more detail. So number one for the RC filters is, let's focus on the low pass RC filters. So from the name low pass, its definition is to remove all the high frequency noise, and the aim is to let the low frequency signal to come in. Okay, so then don't get confused with the high pass. So in the low pass, we want to take the low frequency signal to come in and remove all the high frequency signal. The arrangement, the electrical arrangement is here we have a resistor and we put here as a input voltage, the source, and we put the capacitor. From the name RC filters again, it stands for resistor and capacitor. Then here is our output signal coming out, which have a lower frequency. So from the ratio of the output and input voltage coming to the system, you can see in the graph, it is also available in the book. And here we have what we call as a frequency and a critical frequency. So we have a critical frequency, which is the limit from where we want to remove the noise. Okay, so here we get the critical, the ratio, the horizontal axis is a ratio between the frequency that we wanted and the critical frequency. So we can see that if the ratio is so the ratio of this frequency is getting higher, then we get the output, the ratio of the output input voltage will be lower. So the ratio between output input voltage is written in mathematical equation like this way. It is also written from the book. I took it simply from the book, so you can see that here is our critical frequency, the critical frequency, and if we know what is the input voltage, we can find one of them. Either we can find the output voltage or the frequency. Let's see one example of the low pass filters. So again, from the name filters, you know that it is used to remove the noise, either the high frequency noise or the lower frequency noise when you capture signals. Now a measurement, let's read it together. So a measurement signal has a frequency lower than 1 kilohertz. but there is an unwanted noise. There is an unwanted noise at about 1 megahertz. Design a low-pass filter that attenuates the noise to 1%. What is the effect on the measurement signal at its maximum of 1 kilohertz? What can we know from here? We know that we want to remove the unwanted noise at about 1 megahertz, which is higher, a lot higher than our frequency. Okay, we are measuring something in a very low signal frequency, which is lower than 1 kilohertz. And what we want to remove is the noise above that. And we want to get what is the value. But what we can capture is the unwanted noise is about 1 megahertz. Now we want to design a low pass filter that also remove 1 megahertz, but also remove at maximum is 1%. So 1% above 1 kilohertz. Okay, that's what we want to design. So given the values and given the mathematical equations, we know the ratio between the output input voltage coming from the 1% and the unwanted signal that is captured is 1 megahertz, and we want to find the critical, which is the limit. So it means from 10 kilohertz above will not be considered. Okay. Right, so from here we get the critical frequency, which is 10 kilohertz. 10 kilohertz is 10 times higher than the 1 kilohertz, our measuring signals, our measurement signals. So it means this is the limit where all the frequency above 10 kilohertz will be removed. Okay, the next topic is high pass filters. So it is the contrary to the low pass filters. So from the name high pass, it is used to let all the high frequency signals coming to your system, and remove all the low frequency signals. The arrangement is quite the contrast from the previous low pass filters. The capacitor is put in the beginning, and here we switch between the resistor and the capacitor. So here's the electrical arrangement. Quite a difference, okay? Don't get mixed between the low pass and the high pass. And the properties, the behavior of voltage ratio and the frequency ratio is also quite the opposite, because we want to take only the high frequency signals and remove all the lower frequency signals. Here is also the ratio of the voltage ratio, output, input, and we have the frequency that we want to remove and the critical frequency where the limit is set. The next, number 3 is band filters. So you know already the low pass filters, high pass filters, and now the third is band filters. So it is basically a combination between the low pass. So we can check it out here, the electrical arrangement. So here is a combination actually between the low pass filters and also the high pass filters. So if you combine them together, then you get band filters. So what is band filters? So it aims to remove the high and the low frequency, and we take only the middle frequency signals. And the frequency range in between, we call it as a pass band. Okay. Here in the graph, in the right side graph, there is a signals, let's say in the ratio of in the voltage ratio, it is going up, and then it's normal distributions. If you simply remember in the statistics, it is simply a normal distributions, almost the same, but a bit different. So it is coming high, and finally it is coming down here. Because it is in frequency, the graph will be more or less like this. So we remove the high frequency signals, which is in the right part, and also the low frequency signals in the left part. And okay, sorry. And we remove the left parts, which is the left low frequency signals, and we remove also the high frequency signal. We took only the middle frequency. Okay, so this is pass band filters, or they used to call it band filters. And the frequency range between the low and the high frequency, which is this in the figure, in the graph, in this in between here, we call it as a pass band. So this is the pass band, and this is what we want to take and use it in our system. Let's see an example. Example number 2. A signal conditioning system uses the frequency variation from, okay, now we have a variation. So you can understand that this is a passband filters because the frequency is in a range. It has a range from 6 kilohertz to 60. Remember, this is the frequency. We have also in voltage, okay, to carry measurement information. So our measurement unit or our instrument is able to capture a frequency in between 6 kilohertz up to 60 kilohertz. Okay, that's the meaning of it. Then somehow there is a considerable noise. You know, considerable, it is adjective. Considerable is somehow too much. There's a too much noise at 120 hertz. This is the low. This is the low limit. The lower bound, I used to call it the lower bound, and at 1 megahertz, and this is the upper bound, the higher limit. Design a band pass filter to reduce the noise by 90%. And so it means we have the reduction about 10%, okay? What is the effect on the desired passband frequencies? Okay, so the first thing, we use the mathematical formula from each low pass and from the high pass band, because the band filters is simply a combination of both. So that's why what you see here, the first one is a formula for the high pass band, and the second one is for the low pass filters. Sorry. So the first one is for the high pass filter, and the second equation is the low pass filter. Okay. Now, which value that we should take for these two equations? Right, now let's see the statement here. To reduce the noise by 90%, so the reduction is 10%. So it means the voltage ratio is 0.1. So here is our voltage ratio, 0.1, the reduction. Okay, now we have the limit, the considerable limit that that we want to take. Okay, the measurement signal is 6 up to 60, and the noise is from 120. The noise that we can consider is about 120 up to 1 megahertz. Okay. Remember, in the high pass filter, what do we want to remove? We want to remove the lower frequency, right, in the high pass filter. So that's why it becomes the critical frequency here becomes the lower limit, becomes the lower frequency. It means we take the high pass filter equations and use the lower limit of the noise, 120. Then it gives us 1200 hertz lower frequency limit. And the other way around, don't get confused. In the low pass filter, we will remove the high frequency, right? So because we want to remove the high frequency, the critical frequency now it becomes the higher limit of frequency. Then the noise that we want to consider is 10 to the power of 6. It gives us 100 kilohertz for the higher limit of a frequency. Now, what is the passband frequencies? The passband frequency is these two, between 1200 hertz up to 100 kilohertz. This is what we call as a passband frequency. Number 4, the passband frequency, the passband filter or band filters is type number 3, and number 4 is a band reject filters. Okay, it is the opposite of the band filters. So from the name reject, it means we reject what is in between. Okay, it is one way to remember. So if you see these band filters, so it means we take only the passband in between. But when we come to the number 4 filter, type number 4, band reject filters, so we reject what is in between. Okay, it is shown by the graph in the left picture, in the left bottom picture here. If we have a curve of a signals between the voltage ratio and the frequency, so which parts that we want to remove? We want to remove the inner parts, okay? You want to remove the inner parts, and we take only the lower frequency, both the lower frequency and the higher frequency signals. And the electrical components is a bit quite a combination. If the band filters is simply a combination of both low and high pass filters, but in the band reject filters is quite different. This is quite totally different. Okay, so we have the capacitor, resistor, and the arrangement between these two, it should be connected to the resistor one, and connection between these two resistors should be connected to capacitor and put it to the ground. So the electrical components are quite different. Okay, so we finished with the filtering. We've already learned from the divider circuits, the easiest circuits, the divider. Divider circuits is the basic for the bridge circuits, Wheatstone bridge. We've already learned this on Monday. And we've just finished all the 4 filters from the low pass, high pass, band pass, and the band reject filters. We finished with the passive circuits. Now we are coming to the op-amps. So op-amps is operational amplifiers. Here it is. It is also available in the books. You can read in more details from the book. The location of it is just after the filters. Just the way I'm teaching it is in the same flow as the book. Okay, operational amplifier, or we used to call the abbreviation as an op-amp. The symbol is a triangle like this. So this is a bit more complete. We'll learn the simplest symbol after this. So I'm giving you a more complete version of op-amp symbol. So the operational amplifier, it is symbolized by a triangle like this. Okay, and it has a negative and positive. The negative and positive. The negative side is called as an inverting amplifier op-amp, and the positive node here is called non-inverting amplifier op-amp, non-inverting op-amp. Okay, and there should be a source coming, positive and negative. This is how it is symbolized. And the output is coming from another end of this triangle as an output. So the output voltage will be equal to the A times V. Okay, what is A and what is VO? VO is the output voltage. And what is VID? So VID is the input voltage. So let's see the symbols one by one here in the legend. I plus and I minus, there should be currents coming to the op-amp, both to the inverting and to the non-inverting lines. So according to the signs plus minus, there's a currents coming. The currents should be either positive and negative according to the sign. And the input voltage is also coming here and defined as a V in, the input voltage from the inverting to non-inverting inputs. Okay, and here we have a Vs plus minus, there should be plus minus. This is the source voltage, usually plus minus volts. And the resistors inside the operational amplifier, we don't really discuss this in more details, but it's good for you to know that inside that we have Ri and also Ro for the output resistance. What is important is A, the symbol A, the notation A defines the gain of amplifier. You know, from the name amplifier, it is used to amplify the signals. Ideally very high, it's up to 10 to the power of 10 power of 10 range, okay? Because we use op-amp to amplify signals, of course, the gain should be quite high. So the output voltage coming out from the operational amplifier will be the gain of the instrument itself, the gain of the op-amp times the input voltage. Now the questions, why should we use op-amps, operational amplifier, for our system? Let's say you are designing a system, and do you need operational amplifier or not? We need to understand, okay? Often the signals from transducers are not in the form we would like them to be. So it means the signals could be quite low, and your transducer can capture it. So your system captures the signals, but somehow the signals are quite low or are quite weak, then you want to modify it, okay? They may be, first of all, they may be too small, usually in the millivolt range. This is what I just mentioned, that your signals are too small. So let's say, let's see any practical use. Have you done, I believe you have done practical works, right? Kerja praktek. I believe you have done that, some of you probably. So if you are in a big factory, I was in Cilegon once. I was in a steel company in Cilegon, and they have a big furnace with a very high temperature. And they want to control the change of temperature each time, okay? So let's say if the change somehow in my sensors is quite small in the millivolt range, so it means I need to use the operational amplifier. Okay, and number two, it can be too noisy. Too noisy, let's say again, in the furnace that we want to control its temperature. The furnace is not fully covered. The furnace is not closed. It's partially closed, let's say, the furnace in the factory, so that there are many noises there. There are many external disturbance that may disturb my measurement signals. And usually due to electromagnetic interference. And number three, your signals may contain the wrong information, sometimes due to poor transducer design or installation. Okay, this is because the previous installation is not well designed. And number four, it have a DC offset, usually due to the transducer and instrumentation design. Well, you remember in the previous meetings, in the previous meetings, we have discussed about loading effect. So if we add more and more instruments, then it means you will have more and more gain to multiply, and we cannot refuse the offset coming from the worse instrumentation design. So because of all those reasons, you may use operational amplifier. And how does it look? How does it look? You can see it here. So the symbol is simply defined like this. So if you see somewhere, you see this triangle symbol, then it defines operational amplifier. There's always plus and minus, minus and plus. So the minus is the inverting input and the plus is the non-inverting input. Okay, and the output voltage is always coming out from the other end of the triangle. There should be here, one thing is missing here, the source voltage, the DC source voltage is coming here. But in reality, it looks like this. So inside this, here is some knob that we will connect to another end of another instrumentation, let's say from the transducer or any other instrument. Here is the number 2 coming to the negative, number 3 coming to the positive, and finally the output voltage here coming to number 6. And number six will be connected to another reading device. The characteristics of operational amplifier. This is actually already available in the book, but let's learn together. So the operational amplifier may have 2 supply power, positive and negative. Okay, so actually there should be positive and negative source power supply here coming to the operational amplifier. And there should be a difference, there will be a difference in voltage. So the input voltage with the output voltage, there will be a difference between both. And the V2 minus V1, so V2, V1 is coming to the inverting node and coming to the non-inverting node, minus and plus. We call it as a V2 and V1, right? And this is the input voltage, which is actually, if you remember the previous slides, it is coming from minus to positive. So if V2 minus V1 is more than 0, then Vout, the output voltage, will be negative. And also the other way around, if V2 minus V1 is less than 0, then output voltage will be positive. And this behavior is described by the graph here. We have a V2, V1, and we may call it as a delta V. Okay. So we have the V out, again, if V2 and minus V1 more than 0, then you will get a negative output voltage. This is really up to us. We want to amplify, how big we want to amplify the signals. We want to get the negative voltage or we want to get the positive voltage. Now, an amplifier increases the amplitude of a signal. Remember, amplifier increases amplitude of a signal without affecting the phase relationship of the different components of the signal. So it means that op-amps, the operational amplifier, increases amplitude without any changes in the component of the signals. Okay, it's like we double the signals without changing anything. So when choosing or designing an amplifier, we must consider the size, the cost, how big the signals you want to amplify, the power consumption, of course, the gain and the bandwidth, and etc. So the output voltage that you get, you have seen this in the previous slides. The output voltage that you will get, it depends really from the amplifier gain, which is defined by AV. So we have, this is the amplifier. This is not the correct symbol. We should put it as a triangle, but it is a simplification. We have the input voltage coming to the amplifier. It has a gain. Then it's coming out as your output voltage. The ideal operational amplifier is shown in the figure here. So the ideal operational amplifier is here. We have a triangle operational amplifier. And the positive side, the positive voltage here is connected to the ground. Okay, if it is connected to the ground, then we are sure that the output voltage will be negative. Okay, and there is the resistor coming in from the input voltage, and from the output voltage here is fed back by the resistor 2 to the inverting minus. So from this arrangement, we can find the relation between the output voltage and the input voltage due to these resistors, resistor 1 and resistor 2 is given by this. So we have the output voltage is here. We have two resistor. One is to feedback to the negative, and before that, in the summing junction here, there is a resistor 1 coming from the input voltage. So now, if there is a change in the value of the input voltage, right? If there is a change in the value, if the input voltage is more than 0, the value is positive, more than 0. So our output voltage will be definitely negative because the positive voltage here is put and connected to the ground. And here If the input voltage is quite low, less than 0, and the output voltage coming out will be positive. We learn. I don't give an examples for operational amplifiers. We learn more exercises on Monday. As usual, we will start on Monday, just like today, just in time. We'll start at 4, so we'll have more time to discuss some examples of the operational amplifier. Usually the example of operational amplifiers will be directly to the applications. So here's the op-amp circuits, the operational amplifier in instruments. So it means instruments can be any measuring instruments. Okay, so the operational amplifier can be used as a voltage follower. It can be used also as an inverting amplifiers. You want to invert, or for non-inverting amplifier, or even we can use it as a differential instrumentation amplifier. So we'll discuss on Monday voltage follower, inverting amplifiers, and non-inverting amplifiers. So if I have more examples, exercise, we'll do some exercises also on Monday regarding these three. So the last chapter on Monday will be operational amplifier in instruments. Let's take a look a bit about voltage follower. This is the simplest application of operational amplifier in instruments. Is a voltage follower. It is simply defined by this symbol. We'll take a look in more details on Monday. As the name of voltage follower, it is somehow to follow the voltage. So if the V in is let's say 10 volts, then the V out is also 10 volts. So that's why we call it as a voltage follower. And it is functioning as a buffer. It does not do any amplifications. So amplifier is penguatan in Indonesia bahasa, but in voltage follower it is not functioning as an amplifier. The voltage gain is equal to 1. Right. See you on Monday. We'll discuss this, the last three, voltage follower, inverting amplifier, non-inverting amplifier. In more details on Monday. If I can find some exercises about operational amplifier, I will share it with you and discuss it together in the class. And here is the presency, code of presency. Today we have 27 students, so I'll be reading about 2 minutes. Please to check in for the attendance today, because I will close the class. I will close the presency code once I finish this class. There are 27 students only.
Ma'am, may I ask a question?
Yes.
What does a buffer do, ma'am?
Wait, let me go to the presency. Okay, there are 25 students in presency. Okay, I got questions. Can you again? What is your questions?
Yes, ma'am. What does a buffer do, ma'am?
Okay, buffer. Have you ever heard buffer? Probably some of you. So buffer is used the function. Yeah, the function of the buffer is more to. It is not to amplifying, but it is more to make it clear, to clarify and remove. Uh, it's not a filter, but how can I say? So it is used to prevent the signal affected by the external. How can I say? Like from it. Okay, it is used to prevent the signal to be affected from, let's say, the external currents or any others, but it does not perform an amplification. I hope it's clear.
So, can I conclude that it keeps the signal pure, ma'am?
It keeps the signal.
Pure.
It keeps the somehow yes, it keeps the signal pure, but again, it does not amplify. Does not make it strong signal, or it does not make it weaker signal.
All right, ma'am. Thank you, ma'am.
Yeah. Okay. Right, so there are 27 here already. So there are 3 students not coming. Abdur Rafi is not coming. Muhammad Farhan Al-Ansari and Muhammad Yasir Fadlur Rahman, they are not coming. I will close the class in the presency code. Okay, everyone, thanks for coming. See you again on Monday. Don't forget, I already tell you today, Wednesday, next week, we'll have a quiz before holiday.
All right, ma'am.
See you, everyone. Have a good day.
Thank you, ma'am.
Ma'am.
Thank you, ma'am.